Rao Bhim Chapter 8, Eigenvalues. We are continuing with the same chapter. Now, we have left out certain proofs in the last video, so this video will be devoted to proofs. Theorem 8.3.5, we take any matrix, any complex matrix, square matrix, and alpha is any eigenvalue of A, then the geometric multiplicity of alpha must be less than or equal to the algebraic multiplicity of alpha. So we again have a GM less than or equal to AM inequality. The proof starts by considering this defining equation for eigenvalues and eigenvectors. Since it is an eigenvalue, we must be having some V non-null such that AV equal to alpha V. Now we have already seen that it is quite possible that you have multiple such eigenvectors that are linearly independent. In other words, we consider the eigenspace of A corresponding to this alpha and we take a basis of that. V1 to Vk, they form a basis of the eigenspace of alpha with respect to A, which is nothing but null space of alpha I minus A. So each of these things satisfy this relationship and they are also linearly independent. Now, since I have these for all I, what I can do is that I can stack these things side by side. So I have V1, I have V2, etc., up to Vk. So I get a matrix and I can pre-multiply that with A, in that case by the rule of multiplication of partition matrices. This A will multiply this, separately this A will multiply this, and as a result I will be getting alpha times the first column, then alpha times the second column, etc., alpha times this column. Now this I can write in the following way. I can just take the alpha out as common and then multiply it like this. Now I shall not do just this. I shall do a little additional thing. What I will do is I shall extend these to a basis of the entire space. Suppose A is n by n. In that case I will extend it not to Vk but to Vk plus 1 up to Vn, which will be a basis of Cn. Now I shall do the same trick. I will stack all these things side by side and as a result I will get a matrix which is non-singular. Suppose I call that matrix P. So P has the first k columns given by the basis of the eigenspace and the remaining n minus k things are whatever I need to fill them up. Now I shall do A times P. Now once I do that, this A multiplies all the columns individually and we know this will mean this is alpha V1 alpha Vk followed by just anything. I do not know what this thing is. So U is A times Vk plus 1, Un is A times Vn, whatever that is. I do not have any structure for them, it is something. Now I can write the entire thing in the following way. Remember, I want to take out my alphas. So if I want to take out my alphas, unfortunately because these things are present, I cannot do that easily. So what I shall do is a little trick. I shall write it as P times, the same P times a matrix like this. Now this is something that requires quite a bit of careful thinking and a practice in multiplication of partition matrices. Now why is this true? Because consider P as made up of two parts, the first thing and the second thing. Suppose I call them P1 and P2. So P1 consists of this part, P2 consists of that part, and you are multiplying this with alpha ik 0 0 b. I just said for some b. We will see how we can get that b. Now think of it as if you are multiplying a vector, a row vector with a 2 by 2 matrix. Then this will be P1 times alpha. Remember, multiplication with I has no effect. So basically you get this part, no problem. Now you have to get this part, and P2 gets multiplied with 0. In the second part, it is P2 times B. So all that I have to do is I have to make sure that I choose B in such a way such that I get this equal to this part. So basically I want B to satisfy this thing, P2B equal to U, where this is my matrix U, and which is essentially arbitrary. But that is quite easy because P2 is this part, so they are all linearly independent, so it's a full column rank matrix, so it has got left inverse. So if I multiply like this with the left inverse, then I can always take this to be some left inverse of P2 times U. So such a B always exists. I do not really care about finding a left inverse or finding B. I merely know that AP may be written like this. That's all that I care about. So I can write, taking this P on this side, P inverse AP is this. Now what is the upshot of all this? I started with some A and I took the geometric multiplicity of alpha to be equal to K, because I said that I am taking a basis of the eigenspace and that size was K. So K was precisely the geometric multiplicity of alpha with respect to A. Now I have obtained another matrix which is similar to A. Since it is similar to A, so its geometric multiplicity, algebraic multiplicity, etc., all these things will be preserved. Now look at this matrix. This matrix, if I just compute its characteristic polynomial, that is quite straightforward, because it will be the characteristic polynomial of this, because it's a block diagonal matrix, so it's characteristic polynomial of this times the characteristic polynomial of this. In other words, so characteristic polynomial of this, which is lambda minus alpha to the power k, well, the way we wrote it, we should write it as alpha minus lambda to the power k, followed by this, which means that alpha occurs as a root at least k times. It may occur further as a root inside this part. So I can say that algebraic multiplicity of alpha with respect to this must be at least k. But this is same as algebraic multiplicity of alpha with respect to A, because these two matrices are similar. So I see that algebraic multiplicity is greater than equal to the geometric multiplicity, and this completes the proof. Definition 8.3.6. Suppose alpha is an eigenvalue of A, we shall call alpha a regular eigenvalue if the algebraic multiplicity equals the geometric multiplicity. We always have this inequality, that this is greater than equal to that. If we also have the reverse thing, then we call it a regular eigenvalue. And also we call an eigenvalue of A simple if algebraic multiplicity is equal to 1. It is quite easy to see that a simple eigenvalue must be a regular eigenvalue, because neither algebraic multiplicity nor geometric multiplicity can be equal to 0. They must be at least 1. So if this fellow is 1 and geometric multiplicity is a number strictly positive and also less than or equal to this, and an integer, so it has in that case you must have geometric multiplicity and algebraic multiplicity both equal to 1. But the converse is not true. Now here is the classic example where we do not have equality between algebraic multiplicity and geometric multiplicity. This matrix is counterexample for many results that we shall see later. You can very easily compute that the characteristic polynomial here is 1 minus lambda square, because it is upper triangular. So 1 occurs with algebraic multiplicity equal to 2. So this is my A matrix. Now if you just work out the geometric multiplicity, you will see that geometric multiplicity is equal to 1. So I leave that as a simple exercise. Just directly compute 1 minus 1 times I minus A, and look at its null space, it is trivial to see that it will have dimension 1. So in this case, 1 is not a regular eigenvalue of A. Theorem 8.3.7, suppose I have alpha 1 to alpha k distinct eigenvalues of A and I take some corresponding eigenvector. So this is an eigenvector for this is an eigenvector for this. In that case, this set must be linearly independent. So if you take different eigenvectors in different eigenspaces, they must be linearly independent. The proof will be done by induction. Induction on K. Now if K equal to 1, then of course the result is trivial because eigenvectors by definition are non-zero, and if you have a singleton set consisting of a non-zero vector, then it is linearly independent. So this case is done. So now we assume that the result is true up to some k minus 1, and we are going to prove for k. Now we want to show that this set must be linearly independent. We have assumed already the first k minus 1 are linearly independent. So to do this induction step, we shall employ contradiction. We will assume let if possible Vk be a linear combination of V1 to Vk minus 1. Now we shall employ one result of linearly independent set, namely, if something belongs to the span of a linearly independent set, then it can be written in exactly one way as a linear combination. So let's quickly recall that result. So this is the result. I have assumed that Vi's 1 to k minus 1 are linearly independent. Suppose that I give you two different linear combinations which happen to be same. So some Ai's, some Ci's, they are not part of the proof. I am just reminding you the result. In that case, we must have Ai's equal to Ci for all I. This is what we are going to use. We are going to write Vk as a distinct linear combination of same V1 to Vk minus 1 and get a contradiction. In order to get that, we will pre-multiply, multiply from left by the matrix A. Since all these things are eigenvectors, we have alpha k Vk equal to B1 alpha 1 V1 etc. all the way up to Vk minus 1, because A times Vk is alpha k times Vk. Okay, so now I want to express Vk again as a linear combination of this. So the natural next step is to divide by alpha k. Unfortunately, I cannot do that because I do not know whether alpha k is 0 or not. Accordingly, I will split the proof into two cases. If alpha k is equal to 0, then this side is 0. Now we know by assumption that V1 to Vk minus 1 are linearly independent. Some linear combination of them is equal to 0, which forces all these coefficients to be equal to 0. Now observe that all the alpha i's were given to be distinct and alpha k is equal to 0, which means none of the other alphas can be equal to 0. So all these things are non-zero, which means I can just cancel them off. I can say that B1 to Bk minus 1 are all 0, which means these are all 0, that is Vk is equal to the 0 vector, which cannot be because I know that's a eigenvector and hence it cannot be a null vector. So we can see that case 1 finishes the contradiction. So we come to case 2, alpha k not equal to 0. Then of course we can follow our planned strategy, namely dividing by alpha k. And this gives us yet another linear combination of Vi's that expresses Vk as linear combination of the V1 to Vk minus 1. Now I claim that these and these must be distinct, and that comes from the following fact that at least one of these Vi's must be non-zero. We just now saw that if all of them are 0, then Vk will be 0. That cannot be. So at least one of them is non-zero. Suppose B1 is non-zero. Now all this alpha 1 by alpha k, alpha 2 by alpha k, etc. are not equal to 1 because they are all distinct. So if B1 is non-zero, then B1 cannot be same as this. So I get a distinct linear combination. At least one coefficient does not match. So just look for any particular Bi which is non-zero. You are sure to get one. Look at the corresponding thing. you have multiplied that bi with something which is alpha I by alpha k, and that is not equal to 1. So I have expressed the same vector in two distinct ways in terms of v1 to vk minus 1, which means that these things cannot be linearly independent as I have assumed, so I end up with the contradiction, and that finishes the proof.